Well,
so that's,
step by step. Let's try some simple things first.
but this is much shorter times than acquisition, because acquisition I was measuring 30 milliseconds in the cut-off length, while this periods will be just 7 milliseconds.
Okay, so we're set for tomorrow.
Yes.
The order of events is connector, performance specs. And we're going to ask them to give that to us in writing at the end of the call. That's number one. Number two is the fittings. And then same thing, we're going to ask to get that in writing from them. And what do they need from us to give it to us in writing? You will have the list to send to them.
I will go right now before Bjorn talk, because otherwise, like, Bjorn talk about the long and afterwards we'll spend a lot of time. So go right now if you're done with me.
I am, and I'm writing to both of you right now what I think is happening tomorrow based on this. Okay?
Sure, so Bjorn starts at 2, right?
He starts at 2.
Okay, so then I'll go down. Man, do I have my caliper?
Your good one?
Some, whatever caliper works.
I do not have the metal caliper, no.
But you have plastic one.
Right, but the battery is low.
Our plan for tomorrow.
Ouch. Okay, I'll take it. I should do some.
Our plan for tomorrow is they present specs, and we ask for those in writing.
Mark said he was coming at 1:30 to lecture, correct?
We're
Okay.
going to go over a list of connectors that the boards will supply this afternoon. Dimensions, details. There should be 5 connectors. Quick connect. Broker. Bulge. Broker. Well, my one question is, what do we want at the end of that? We will go into another one of those like master. I guess we can cross that bridge when we come to it.
We have no idea what that thing is.
I think it should be drop that from us. Because over time.
Right, because that would become part of whatever purchase we were having from them to buy.
No, I think you're right.
Because otherwise we have really no clue as to what it is.
Number 3 is delivery time. Delivery time. Common dimensions. Weight. Power requirements. Input error requirements. Warranty. Negotiate price. Okay, I just sent you what I think we just agreed on for tomorrow, okay?
Okay.
Hopefully it'll look familiar to you. Super steady. Hi.
Talk about this.
Art said he wanted to go over something today with you at 1:30. So why am I here? Well, I'm just here because I like Mike. That's why.
I just had something I was going to do on my phone and it was right out of my mind.
I'm sorry. You guys got something to read from me for tomorrow, and a notice that tomorrow's class has to be short, partly because today is so long, and partly because we have so many visitors this week. So tomorrow we're going to start right on time at 1 and end a little bit before 2, like a normal 15-minute class. And it's related to the last lecture I gave, whenever that was, last week. The cross-polarization pulse sequence and the theory describing it. And we're going to finish taking that theory up to the point of a publication, like the full experiment, hopefully. One hour will be enough. So if you go over your notes from last time and look at that paper I sent, that will help you prepare for tomorrow's class. Who scheduled you? Who scheduled you? Locking the cats in the bathroom and cussing. So typical. So typical. It had to be this week, right? I love it.
Finally remembered.
See, that helped you.
Yes.
Memory is a funny deal. All right, let's do this.
I'm just going to use the
Hi.
Can I help you with anything, or?
Which of my many problems would you like to solve?
Something time sensitive, of course.
I have 37 ridiculously complicated statistics problems. That's the great.
Oh, so it sounds like Keith wants us to volunteer.
Yes.
So are you good with ride designs or
Yes.
and the HFR? Do you like that?
Yes, that's fine. Yeah, that's fine.
Do you have anything you want to plug for?
No?
I thought it wouldn't hurt us to review part of the latest DHFR.
So what I wanted to do quickly before Baron starts, oh, do I need the mic?
No, it'll be okay.
Okay, is what we haven't really done so much is, for solution anyway, kind of design and analyze pulse sequences. So I wanted to get started on what will be the next problem set, so I'll get you started on it. It's a problem set developed by Stefan Zeszek. And what we want to do is design an HNCO experiment. And the acronym means we're going to start on the amide nitrogen, transfer to the amide, or start on the amide hydrogen, transfer to the amide nitrogen, to the carbonyl, and then go backwards. And we'll label for a 3D experiment, label the carbonyl chemical shift, the nitrogen chemical shift in the two indirect dimensions, and then record the hydrogen frequency. And in the beginning, when people did these, it was kind of random. In the two indirect dimensions, T1 and T2, it would be kind of random whether the nitrogen was recorded first and then the carbonyl frequency, or the reverse. And now it's more traditional, as we'll see as the problem develops, to transfer through the nitrogen the first time, record the carbonyl chemical shift in T1, go back to the nitrogen, record the nitrogen shift in T2, and then go back to the hydrogen. So we'll do that. We'll pretend we already knew that there were reasons for preferring that, even though that won't be obvious for a little while. And just to remind you what it is that we're talking about. Here is, say, amino acid I in the sequence, and over here is amino acid I-1. So our plan is to move magnetization from here to here by that one bond coupling, and that coupling is about 92 Hertz. And then from here to here, that coupling is about 15 Hertz. We'll record the chemical shift of the carbon, and then transfer back, record the chemical shift of the nitrogen, and then transfer back to the hydrogen for detection. So all of these kinds of experiments are called out and back experiments, because the magnetization goes out and then it comes back. And you'll see that these are mostly just catenating together a bunch of inept transfers.
Can I ask a question?
Mm-hmm.
Is there a particular advantage for always tying yourself to that amide proton? Either the out or the back direction. You don't necessarily digitize anything, so you could get to whatever the closest proton is. Depending on how you deuterated your sample or whatever, is it ever advantageous to use something other than the amide proton?
So there are now, historically, things have been done this way because, as Anne mentioned about cross-polarization last time, the hydrogens have the largest polarization, so they have the most magnetization. And because their magnetogyric ratio is large, they're the most sensitive nucleus for detection. On the other hand, there are relaxation problems that can be associated with the hydrogens. So, for example, if we replace this hydrogen with deuterium by putting the protein into D2O, the relaxation of the nitrogen 15 is going to be reduced theoretically by a factor of roughly 36. So the lines, the nitrogen lines, are going to be intensely narrow. So one might think if you had a real, but the magnetogyric ratio is low on the nitrogen. But you might think that if you had a sensitive probe for detecting nitrogen, it might be possible to come out ahead nonetheless, particularly if we start to think about Trozy type effects that we haven't really talked about yet.
Or coming in out on the H alpha.
The H, well, I was going to say the same argument can be made about the carbonyl. There are also now experiments that would do direct detect of the carbonyl, so you wouldn't go out. You could start here, go to the nitrogen, end up on the carbonyl, just record its frequency. One of the downsides of doing that is just kind of a direct experiment is the carbonyls typically relax quite slowly, so you have to wait a very long time. But in this case, you don't care because you're starting with the polarization of the hydrogen, and you know that may come back quite quickly if there's methyl groups around, etc., as Ann talked about. The H, detecting on the H alpha or starting on the H alpha.
Like on the I-1, so it's the same number of steps.
Has the downside that the H alpha relaxes the carbon very rapidly. So there are experiments that start there, that start on the H alpha, but for assigning the backbone of the protein, which is kind of always the starting point, those are hardly used anymore in solution, because typically what we might do is grow the protein in D2O so that this is deuterated, and then the carbon relaxation is also greatly reduced, and then we can sit magnetization on that carbon for quite a long time. Otherwise, we're very limited in how long you can sit magnetization on this carbon. So we don't have at the center right now probes that will do high sensitivity detection of the nitrogens or carbons, and there's some discussion of writing a shared instrumentation grant jointly with people at ASRC to rectify that. So we have then pulses are going to be applied to the 1H spin, pulses that will be applied to the nitrogen, pulses that are applied to the carbonyl, and we may need pulses applied to the C13 alpha. Because there is coupling here, so we're going to have to do some decoupling. The coupling over to this C alpha over here is 55 hertz over to the next C alpha. The coupling here is probably of order 12 hertz or so, and there's also a two-bond coupling over to this alpha that's a little smaller. So we're going to have to do some decoupling. And what we just want to think about right now is the simplest possible experiment. And then when you go on, this will hopefully help you finish the midterm. But then when you do the next problem set, you'll turn this into a better, more modern experiment. So if we're starting here, we obviously have to start with a 90-degree pulse on the hydrogen. So suppose that was X phase. What kind of magnetization will we end up with? Minus Y. And now we're going to use an inept sequence to transfer the magnetization. So we want to evolve this coupling and refocus all the chemical shifts. And as you saw in the last problem set, then we need a spin echo with 180-degree pulses on both nuclei. Everybody remember that from the last problem set? So here, I'm going to have some delay tau. These simultaneous pulses will allow the nitrogen coupling, the H to nitrogen coupling to evolve, but any couplings to the carbons will be refocused, right? Because there's not a pulse on these nuclei, there's only the pulse on the hydrogen. When you think back to the previous problem set, that would just refocus the proton chemical shift and decouple, or refocus these couplings. So at the end of this period, I have a period 2 tau. The term I'm interested in is going to be the antiphase magnetization. So under the coupling, this will evolve, right, towards 2IX NZ, if I use N for that. And that term will then, if the delay is 2 tau, it'll go as sine 2 tau pi j for the NH. If I want to maximize this signal, ignoring relaxation, what do I want the sine term to be equal to? What's the maximum of the sine function? Not a hard question. What's the maximum of sine x? 1. So I want this to be equal to 1. So that means all of this has to be pi over 2. Or tau has to be 1 over 4j. So I know how to set this here. Tau is 1 over 4j nh. And I end up then with pure magnetization in this antiphase term. I may need to deal with relaxation effects. Those will come later. Now what I want to do is convert this to antiphase magnetization on the nitrogen. So I want to turn this into 2IZ, let's say NY. So what phase pulse do I need on the hydrogen? I want IX to go to IZ. What phase pulse? Oh, we'll take IX to IZ. A Y will take X to minus Z. Well, I actually don't care about the sign, so I'm just going to make it a Y pulse. And now I want to take NZ to NY, and an X pulse will take it to minus NY, so the two minus signs cancel each other. So now I've transferred in the first net to NY magnetization. And now I want to transfer this down to the carbonyl. And I just have to do the same thing again. From my standpoint, now this pulse took NZ magnetization to NY magnetization. That's the same as what happened here. I started here with IZ magnetization. This pulse took IZ to NY. So if I think of this as being analogous to that, I just have to replicate this whole block now on nitrogen and carbonyl rather than nitrogen and proton. So here's this. I need a new tau. Let's call it tau 1 and use a better marker. I call this tau 1. 180 on the nitrogen. Now I want the coupling to the carbonyl to evolve, so I need the other 180 here. Another tau 1. And then I expect, by analogy, I'm going to need a Y pulse and an X pulse, 90-degree pulses at the end. How do I set tau 1? So tau 1 now needs to be 1 over 4j NCO to make that work. So the taus will be different for the different NFs, but the pattern is the same. And I expect here to, well, what do I expect? Well, first of all, let me worry about some of the other couplings. I have this IZ operator. What couplings could evolve? I don't have any pulse on the hydrogens. So to the extent that there's, say, a carbonyl coupling, it's going to refocus. The only transverse magnetization I have here is carbonyl, so I only have to worry about couplings to the carbonyl group. If there is a coupling from the carbonyl to the amide hydrogen, it's going to refocus because I don't have a pulse on the hydrogen. Turns out the coupling is pretty small, I probably wouldn't worry about it, but in any event. And then couplings to the C alpha would refocus because I have a pulse on the carbonyl but not a pulse on the C alpha. So what am I going to end up with here? I'm going to have now 4 IZ, because nothing happened to this operator. There was no coupling that evolved under. And then I'm going to have NX. Oh, but I flipped it up to Z. And then C prime Y. That's what I have right here by direct analogy to what I had here, except this IZ operator just came along for the ride. Nothing happened to it because all of its couplings were refocused. Now I'm in business because what I wanted to do was get transverse carbonyl magnetization so I could record its frequency. To record its frequency, I now need a T1 period that I'm going to increment in order to measure the frequency of the carbonyl spins. So T1 will start small, and then it gets incremented up as I fill in the two-dimensional experiment. So that's fine. I'm going to increment T1 by some value delta T1, and I know that delta T1 is going to be 1 over whatever the spectral width is for the carbonyl spectrum. How do I know the spectral width for the carbonyl spectrum? How do I know how wide the spectral width is for the carbonyls?
Do you mean
Pardon?
Do you mean how do you control it in the pulse sequence?
No,
Or do you
how do
mean-
I know what the chemical shifts are of the carbonyls?
Statistic.
I mean, I'm a new graduate student. How do I know what the chemical shifts are? What are the possible chemical shifts for carbonyls in a protein?
So for chemical shift, that is online data. You can look where is the CO from 160 to 180 something.
Right. So how did you know that? Okay, so these days there's a database of chemical shifts, right? So I could go to the database of chemical shifts and look and see what they are. I may want to fine-tune that for my protein. So of course I might run a short experiment with a wide spectral width and then adjust it. One of the problems that can come up in these experiments is which direction of the frequencies are positive and negative. How many of you have collected an HSQC experiment? So in a nitrogen HSQC, right, you have a bunch of peaks. But how do you know which the top and the bottom is? There's something very distinctive in an HSQC that you can tell if you're looking at it right side up or upside down.
So normally I also set a wide spectrum for set a big value for SW and measure spectrum, and then I don't know what are the signals, and then I calculate using the cover frequency.
Right? But if I have it upside down, making it wide doesn't necessarily help. In the HSQC, there's the side chains. Right? You see the side chain amides up here, right, in this kind of distinctive bunch. If you process the spectrum and they end up down here, you say, I just processed the spectrum wrong, and then you reverse the axis, or you take the complex conjugate before the Fourier transform. If I didn't have this feature, then I can open up the spectral width a lot, as suggested. But then to make sure I know, I should put the carrier down here, or the carrier up here, so that I know everything. If I know the spectrum is supposed to run from, say, 100 to 130 parts per million, if I put the carrier at 90 and make the spectral width very wide, then I know I should see everything in the lower half. And if it comes up in the upper half, then I know I have to reverse the spectrum or change one of the pulse phases. It's not a problem with nitrogens because we can always find these. But the carbonyls, there's nothing distinctive that tells you which is up and which is down. There's no obvious asymmetry in the spectrum. So when you do this experiment for the first time, it's useful to put the carrier, what you think is the one edge, open the spectral width way up, and make sure that when you process it, you get the spectrum where you think it should be. Then you can move the carrier into the middle and cut down the spectral width for the future. And in fact, we once deposited a set of shifts in BMRB where all the carbonyls were flipped upside down. So now I'm very careful about this, because depending on the exact phases here that people picked, it could be flipped relative to the way that you normally process your data, because there's options when you're processing the data about how you do the Fourier transform, etc. And it's easy to have things get backwards. You hardly notice this for the HSQC, because anytime you see the amides at the bottom, you know you have to flip it. And NMR pipe has a reverse command to make that very easy. But in the carbonyls, it's not so easy to tell. Anyway, that's just a warning. What about couplings? If I just do this, I have transverse carbonyl. What couplings are going to evolve? And how do I decouple them? So there's going to be a coupling from the CO to the C alpha. 2 minutes. Yes. If I want to decouple that, I can put a pulse in the middle. Okay? Now I have a pulse on the C alpha, but not the carbonyl. So I won't refocus the chemical shift, but I'll refocus the coupling to the C alpha. What about carbonyl to nitrogen? There's a coupling, 92 hertz. 15 hertz. And I can get rid of it by putting a 180 in the middle on the nitrogen. And then I have to decide whether I'm worried about the coupling to the hydrogens. If they're only a couple of hertz, I might figure, who cares, I'd rather take it easy on my probe and not put in more pulse power, and leave the pulse out and live with the 2 hertz coupling that I'm never going to see. If I thought it was 10 hertz, I could always add a 180 here. And now, this is as far as we'll get today, now I'm just going to go backwards. I'm going to reverse all of this, except at some point when I have transverse nitrogen, I'm going to put it in the T2 period, so I can record the frequency of the nitrogens. So in my next inep, here I want to go back to nitrogens. So at this point, I will have brought the magnetization back to nitrogen. I can put it in the T2 period, worry about what 180 degree pulses I need to decouple during the T2 period, and then have a 180 in that period back to the hydrogen, and then record the signal. So it's completely symmetrical, except that I've inserted these T1 and T2 periods in order to record the frequencies of those nuclei. But it's 4 ineps. Hydrogen to nitrogen, nitrogen to carbonyl, carbonyl back to nitrogen, nitrogen back to proton. Magnetization flows out, magnetization flows back. This will generate a perfectly fine spectrum, and then the problem is, really, how do I get the narrowest line shapes and the most sensitivity? Basically now, how do I fight relaxation and make this sequence more efficient? But that will be part of the problem set. You won't need that kind of information for analyzing the midterm. The midterm basically asks you to kind of walk through this kind of process. It's not as long a pulse sequence, but it's the same kind of analysis. Hopefully that's some hint. And then, like I said, the next problem set starts here, but then asks you piece by piece how you would gradually make the sequence better and better, more and more modern. So, quick questions before we let the crowd in. Yep.
Is it tau 1 over 4G or 1 over 2G?
Well, here, because I put tau in twice, and then I have a 2 here, it's 1 over 4J, but the whole period will be 1 over 2J. Because there's 2 taus. This whole period is 1 over 2J.
Oh.
But I wrote it in pulse sequence. Sometimes you'll see this as tau over 2, and sometimes tau and tau. So 1 over 4J versus 1 over 2J. The spacing between the two 90s has to be 1 over 2J. Other questions? Well, can you tell Anne she can let